Hi guys! Today I want to tell you my story about building a low battery switch based on a microcontroller in times of part shortage in 2021 till 2022. For a battery-powered DIY project, I wanted a switch that switches off the load when the battery voltage drops below a certain voltage. This was necessary as a lithium-ion cell-based battery pack was involved. To keep the cells healthy, special care is required. The logic flowchart looks like this. First, the MCU tests the battery voltage. This can be done with a comparator or an AD converter. Then it is determined if the value is above or below the limit. If it is below the limit, an LED should flash for 1 minute as a pre-warning, so I can take actions to prevent ruined video material. Then the MCU again tests the battery voltage to make sure that the low level is steady and was not caused by a short brownout. Now it is again determined if the value is above or below the limit. If it is not, the process waits and then jumps back to the start. If the value is below the limit, the output is toggled. That means that the output is turned off permanently for an external NMOS transistor. After this, ultra-short flashes of the LED indicate that the unit is still turned on, with only the low voltage switch turned off. The short pulses save precious energy to keep the load on the battery as low as possible. The LED indication itself informs me that I still have to turn off the supply. As I was aware of the parts shortage, I started to look for an MCU to work with. The PIC microcontrollers I usually use for this were out of stock. Let's have a look how the situation is today in October of 2022. I look for the PIC 18F45K22. Okay, here's the chart. The IPT variant I would use is still out of stock. Even the other variants are affected, so you don't have a chance to use another package to save your project. Let's have a look on the variant page itself. Now let's see what the lead time is. I do it for 10 parts. Okay. 24th of April 2023, so still over 5 months to go. The situation hasn't changed. Even today I had to search for alternatives. So I turned to Atmel microcontrollers because I hoped the situation is better there. After some research at a random dealer, I found out that a few models are actually available. A quick check raised my attention on ATtiny12L. This is a legacy low-range microcontroller with only 1K of flash memory, but I was sure that this would be the right part for my simple application. Even in C, this simple program would fit into 1K of memory. That's the datasheet of the ATtiny12 and 11. The 11 has no EEPROM and misses also other functions. You see that I have written some clue notes in the document for an easier workflow. Here you see the pin configuration of the ATtiny12, 8 pins, VCC, GND, reset and 5 pins for port B. Page 6 shows that the ATtiny12 has an internal RC oscillator of 1.2 MHz. Page 41 shows the details of the comparator. Even a bandgap voltage reference is available and can be digitally connected to the plus input of the comparator. This is useful for my application because I have to test for a specific voltage limit. Page 73 shows the current consumption. In active mode, when using the internal RC oscillator, the current is 700 microamps. In idle mode, when using the internal RC oscillator, it's impressive 260 microamps. That is very low and very good for battery-powered application. Seems to be the perfect choice. But page 4 shows the block diagram of the ATtiny12. If we have a closer look, we see that there is no SRAM. So no RAM for variables, etc. What a bummer. Due to this fact, the C compiler I intended to use does not support the ATtiny12. And I was not able to find a decent budget-friendly C compiler which supports it. So I was stuck. The only chance to program the ATtiny12 was to write assembler code. And I am far away from being an assembler nerd. Assembler is very hardware specific. You have to do all steps on your own. No help from the compiler to be expected. As a workaround, I wrote the C code and tried to analyze the disassembled assembler code from the compiler. This was good to get a first glance of the code structure, but the more I looked, the more question marks appeared in front of me. Especially the lack of RAM makes it necessary to dive deep. Luckily, a friendly guy was kind enough to write the assembler code for me. While discussing the function details, I learned a lot from this, but I still prefer C as my favorite programming language, that's for sure. But then the next surprise popped up. The USB ASP AVR programmer was not able to program the ATtiny12. I don't know why. I tried another chip, tried to change the supply voltage from 3.3 to 5 volts, soldered even a Tinker wire to enable the slow programming mode, but all I tried to solve it failed. Again, the friendly guy stepped in with his professional Atmel programmer, but even he struggled a lot to get the ATtiny12 programmed. But with a lot of patience, a lot of timeouts, just 8 kHz programming clock, and overwriting the flash several times, he managed it. After this experience, I will not use the part again, ever. It's obviously too old. After I had the programmed MCU in my hands, I started to develop a schematic diagram. Nothing special. The MCU, a voltage regulator, a voltage divider, a MOSFET for switching, and an LED for the indication of the function. To make a first test, I soldered one chip onto my SO8 programming board. The left LED indicates the state of the MOSFET output. The right LED indicates the status of the circuit. I use the potentiometer to provide a variable input voltage which represents the battery voltage. If I turn the circuit on, the MOSFET output is high. When I lower the input voltage, the right warning LED starts to flash. Everything works as intended. Now I was motivated to do the real circuit board. It was necessary to make it as small as possible, so I have built a kind of dead bug style SMD board. It will not win a design award, but it is a kind of art and it works. Finally, I integrated the circuit board into my tiny housing. The circuit cuts the load off at the voltage at 10.6 volts, so the cell in the 3S1P lithium-ion battery will not experience a voltage lower than approximately 3.5 volts to avoid a deep discharge. If I get sufficient response from you guys, I probably cover the main application to which the circuit is mounted. Please donate to help me out of trouble. My PayPal address is donatesurfloose@gmx.net. Any help is appreciated. If you're not already a valued subscriber, you now have the chance to become one. Like, comment your thoughts and stay tuned for more videos. I will see you next time. Bye bye.